So I recently was visiting my family for Thanksgiving, and my niece, my adorable 7-year-old niece, asked me one of those questions that kids like to ask. She said, "Why is the sky black at night and blue during the day?" And I said, "Well, at night, the sun's on the other side of the planet. There's not any light, and that's why it looks dark. But why is it blue during the day?" I don't know. I guessed, oh, maybe it has something to do with the oceans, because I'd heard something like that. But I didn't know. And I felt very embarrassed, because I am 42 years old. And in all those years, I never learned the answer to such a basic, simple, childish question. Why is the sky blue? I couldn't believe I didn't know the answer. So I spent some time looking up information on the internet, trying to get a handle on it. And I learned a lot of really interesting, fascinating things. So I wanted to come talk about it. So to start with, we got to talk about light, which is a very tricky topic. I'm not a physicist. I don't know all the real details of everything that's going on. It's all a bit mysterious to me. But essentially, every object emits light, for lack of a better word. And what is light? It's kind of like energy, maybe, or it's a wave, or it's a particle. People use all these words. It's very difficult to wrap your head around what it is or isn't. I think of like a laser beam. That kind of gives me a good idea of what light might be, kind of. It's like it goes in a direction, kind of straight. Sure, little things could bend it or refract it, reflect it, but it's kind of like a pathway of energy, maybe. I'm not sure. Anyways, it tends to go off in every direction. Like when you shine a flashlight on something, it lights up and that light shoots out in every direction. But here's the weird part, is that not all light is visible. Most light is not visible, actually, which is really, really weird. So for that reason, I don't really like calling it light, actually. Because when you say light, you think of, the stuff that you see. And that's kind of, in your mind, the definition of what light is. If a room was dark, you can't see anything, you would say there's no light in it, even though there is this sort of stuff in there. So they have a different word for it. They call it electromagnetic radiation. And I really dislike that also. For one thing, it sounds like really pretentious. Electromagnetic radiation. What the heck? It makes you just want to roll your eyes or fall asleep. Kind of a ridiculous name. Electromagnetic. Oh, it's something about electricity and magnets? What the heck? That doesn't seem to have much to do with it. Radiation, that makes you think of like nuclear radiation, like this deadly kind of contamination of things. But it doesn't really have much to do with that. It's like its own kind of radiation. So light makes you think of things you can see, which it is not. And radiation makes you think of things that are like deadly, which it's generally not. It could be, I guess, but at certain intensities. But I don't know. I feel like we need a new word. It's like a magical laser energy transmission beam or something. I don't know. I don't know what to call it. Light, huh? So basically, all objects emit this sort of light stuff, and it always travels at the same speed, famously called the speed of light. No matter how powerful the light is, it all travels at the same speed, which is kind of crazy. And the only real distinguishing feature between different beams of light would be like how intense they are, how much power is in them, which is also described as frequency, which is again a word I don't really like, and power I don't really like either. All these words are so like overloaded and confusing, it can be hard to understand what they're even talking about. But frequency is like, if light has, it's kind of like vibrates as it goes, and frequency is like how fast it's vibrating, and it's also how much power and intensity it has. So because all objects have a bunch of electrons and molecules that are bouncing around and interacting or whatever, they're always emitting this light stuff. It's just that most of it is so low intensity that it doesn't reach the level where we can see it, which is called the visible spectrum. So it's well below that. And there's like different names of different sections of the frequencies below the visible spectrum, but it makes sense to me to just think of them all as one like low energy invisible light. So I think of like a coil that heats up, or any object that you kind of heat up, like in a fire or something. At first, as it's getting warmer, it doesn't look any different, but then at a certain point it starts to glow. They call it, it gets red hot. It's so hot that now it's glowing with this red light, this light's coming off of it. And the truth is that light was coming off of it the whole time. It's just that when the heat got high enough, the light coming out entered into that portion of our visible light spectrum, which, by the way, the light being visible has nothing to do with the light itself. It has only to do with our own eyeballs and us as human beings, how we evolved and what we can sense. So visible light isn't actually physically special in any way. It's just something unique to us as humans, what we perceive. So it turns out that the creation and emission of light is also related to heat. So how hot an object is determines the frequency or the power level, the vibrational speed of the light that comes out. And they call this black body radiation, which again is a weird name that I don't really like. But it's like, okay, if there was no other light shining on this thing, it was a black body, then how much light does it emit or radiate just on its own, based on the molecules and electrons bouncing around inside of it? And most things that are like at room temperature or whatever, they'll be emitting very low power beams of light. But things that are very hot can emit more and more powerful beams of light. And the interesting thing about it is objects don't emit just one beam of light, one frequency or one power level. It emits like all of them. So if it has like a power level of 10, then it's also giving out light of power level 9, 8, 7, 6, 5, 4, 3, 2, 1 all the way down. So now you think of well, again, if you think of a coil that heats up, it gets red hot, and then if it gets even hotter, what happens? It becomes white. So as it gets hotter and hotter and hotter, it starts with the red, and then it goes up through the other colors, but they all add into the red, so the effect is it just builds up more and more towards white. Then it gets white hot. And then as it gets even more hotter than that, then even more powerful light beams come out, but we can't sense those because they're too high, too much power. And that's what the sun is doing, because the sun's so freaking hot with all the nuclear explosions going on in the sun. So it emits all the types of light. And the first type of light that we can see that's visible is red. And then the higher frequencies we can see have different colors as well, and that's what a rainbow is. So when you look at a rainbow, you can see all the different bands of color. That's all the different frequencies of light getting split up, and so we can see them individually, and you can see that there's red, orange, yellow, green, blue, indigo, violet. I don't know, that indigo violet thing, I don't get that. That seems all the same to me, just purple. Anyway, the point is, that red is actually the lowest intensity light that we can see, which was really confusing to me because that's like the opposite of a rainbow, right? A rainbow starts with red at the top, and then it goes down through yellow, green, and then down to blue at the bottom. So I thought, blue's the bottom, red's the top. So in my mind, red is the most powerful, but that's not right. Another thing is that in art class, they always taught us that red is like a warm color and blue is a cool color. So red is the color of fire, but blue is the color of the ocean and the sky, which is cold when you go up in the sky, like on a mountain or something. So blue feels like it should be like a cold color. But in reality, it's the opposite. Blue light is actually the most intense that we can see. And red light is the least intense that we can see. But there's actually light intensity that's lower than red, and that's why they call it infrared. So I've heard of this before, this infrared thing, like there's infrared goggles where you can see in the dark. Well, yeah, that's because any object with any sort of temperature emits these light beams that are lower power than what we can see in the visible light spectrum. So that's called infrared. Or there's some even lower power ones that they don't call infrared, but I'll just call them all infrared because it makes sense. So infrared is like below red. And even when you see a rainbow, like, on a rainy day, you see a rainbow in the sky, it's got all the colors in the visible spectrum. But there's also infrared. So above the red, there's actually going to be infrared bands that we can't see because they're not visible to us. But if you use special equipment, you can see them. Similarly, if the power level goes above the blue, which is the other end of the rainbow, like inside the rainbow, then it becomes ultraviolet, they call it. Ultraviolet. And I've heard that term too. That's about, you go outside, you want to put sunscreen on so you don't get UV exposure, ultraviolet light exposure, because it damages your skin. And the reason it damages your skin is because it's so intense. It's very high intensity light. And it can interact with the molecules on your skin or underneath your skin and cause damage and sunburns and cancer and all that stuff. So it can be dangerous. That's ultraviolet. And then there's a bunch of sections above ultraviolet, like X-rays and gamma rays, but it's all similar, it's ultraviolet, above violet, very intense light. And that's why when you go to the dentist, they give you the X-ray, which is like a very intense ultraviolet light. And you have to put this like lead apron over your body so not too much of it goes into your body because it can cause damage. And that's in that ultraviolet kind of section of light intensity. So yeah, the sun is so hot, it's emitting all sorts of power levels from the very low to the very high, and they're all coming to Earth, getting beamed over here on these light energy rays. And they all kind of mix together, all the frequencies in the visible spectrum, so it looks white to us. People say the sun is yellow, but it's really kind of white light that's coming out. It's just that the yellow frequency is, I guess, the most intense because of exactly how hot the sun is or something like that. But yeah, it looks generally white, and then as it comes into the atmosphere, if there's water droplets, it can split out like a prism, I guess, and create the rainbow. And it also has ultraviolet sections of the rainbow that you can see with special equipment. So anyways, why is the sky blue? All that is to say, basically what's happening is this phenomenon called Rayleigh scattering, which is a stupid name. I don't like it. It's called Rayleigh because there's this guy named Rayleigh who died like over 100 years ago, and he's some scientist or something. And it's just annoying to me because to explain this phenomenon to a child, which anybody all over the world could wonder, why is the sky blue? Now we gotta bring up some individual guy, Rayleigh, and talk about him. It's just extra unnecessary work. Who's this guy? Why does he deserve to have everyone know his name? And now you gotta learn extra stuff. I just don't like that. You might say, no, it's okay. We learn about history and learn about where it came from and all this stuff. I guess, but we only have so much capacity to learn information, Why waste it on trivial, unimportant things. You know, he didn't create this scattering, he just named it or discovered it or whatever. Anyways, that's just the way it is that it's called Rayleigh scattering. And what happens is, as the visible light from the sun comes into the atmosphere and the air is made up of all these particles, right? And the different frequencies of visible light move through the atmosphere, but the most intense ones, like the blue light or the ultraviolet light, they are vibrating faster, so they have more chance to hit and collide with the air molecules, because the air molecules are so spread out. You know, light doesn't hit them very often, but if it is going to hit them, it's more likely to be hit by the blue ones. So when a light beam hits an object, it like scatters, it shoots off in another direction. So as the light comes into the sky, all the blue frequency light hits the air molecules and scatters off and creates this blue color. Meanwhile, the red light, it takes longer to hit the molecules because the red light is lower intensity, lower power, lower frequency. It doesn't vibrate as much. So it's not hitting the molecules as easily. So it actually, on average, takes longer to get hit and scatter off. So that's why when there's a sunset, the sun's really low. Now it's coming kind of through a bunch more atmosphere as it's traveling over the mountains and everything to where you are. So in the sunset area, you can see that there's a lot of red light, orangish light, yellow light, all sorts of these other colors, because the blue already got scattered away when it entered the atmosphere so far away, and it kind of showed the blueness to everyone in that section of the earth. And then as it got to you, now you're seeing all the red light that's left as it slowly gets scattered over the long distance of the atmosphere. Which is to say that the sky isn't always blue. Like, look at a sunset. The sky can be red, it can be yellow, it can be a lot of different things. It's interesting in context of the sky, there's really kind of only two main colors. There's red and blue. Red being like the low intensity light and blue being the high intensity light, and then they kind of like transition between each other. It's not like a full rainbow where there's like green. There's never like a green sky. And as stuff heats up, you never like see the green color because it's adding all the different light wavelengths to each other, going from red all the way up to white when the blue gets added, you see. So that basically explains why the sky is blue. Maybe that's too much for a 7-year-old to understand all that, but maybe they could, I don't know. It is a lot to say for such a simple explanation, but it did connect to a lot of these concepts that I've seen in life, like X-rays and infrared and ultraviolet. So all that seemed cool. And plus the fact that it was the opposite of my intuition, where I thought red light is the most intense and blue light is cool and less intense, but it's actually the complete opposite. Blue is like crazy intense light right near ultraviolet. And I didn't know that, and now I know after learning about this stuff. So maybe you'll find that interesting too, and you know a little bit more about how the world works and a little bit about physics and light, stuff we deal with every day. Not even if you're not a physicist or interested in science really, it's good to know some basics about the sky and just basic simple questions that even a child would ask. So I hope you found that as interesting as I did, and see you next time.